Thank you also for choosing very nice date for my presentation, 12/12/12, very nice date. I'm engineer, I'm not mathematician. Then maybe I will show you another point of view to the fuzzy logic. I'd like say a few words about implementation. Then if Professor Novak was spoken how we are thinking, and he also mentioned that what we like to do is to learn this way of thinking also machines. That it is Czech famous writer Karel Čapek who proposed the word robots for the thinking machines. Then from, I think this is the older idea of us to implement this kind of thinking to the machines. Then I'd like to present which tools we have today for this implementation and what are the bottlenecks of these tools, and what brings new nanotechnology today, how to overcome these bottlenecks. Oops, sorry. Which one is next slide? The next slide, which one? It's another one. Sorry. Yeah, thank you. Not this one. No, this one. No, not this one. Which one is you have used? No, it doesn't work. You are thinking in the same way as me.
Okay, and I think the next.
Okay, this one is next. Okay, thank you. Then what I will talk about this fuzzy logic system and its implementation, and I will concentrate to the specific fuzzy logic system with direct input and direct output, like in Sugeno system. Of course, we have some rule generator, which means a machine which will generate the structure of the inference engine. But we may have two types of fuzzy logic system. One type is with flexible rule generator, when we can generate new rules. But another type, which is very suitable for practice, is also the fuzzy logic system with fixed rules, which were learned before application. Then today we have main two kinds of implementation, because the most intelligent machine what we have today is computer. Then very common implementation is by software. Then we write some rules and then translate it into a program, and this program is done by the computer. Another implementation, what may be the hardware implementation, and I will again mention the bottlenecks of these two types of implementation. What we have today in software implementation is implementation into von Neumann concept of computer. And this concept have some bottlenecks, because the main difference between the first computer, ENIAC, is that ENIAC, the program was given by wiring. These women write the program just now if they put the wires from one block to another block. And this is what was changed by von Neumann when he decided to put the program into memory, and in each step we take one instruction, one piece of data, we calculate that and put back into the memory. This is von Neumann concept of computer. But as we can see, this is serial machine, then we can take only one separated instruction and then next one and next one. But today it is a bottleneck, because we need calculate more data in parallel to obtain the higher performance. Then what we can do? Of course, what we are doing today is that we take more CPUs and we calculate data in more CPUs in parallel. But it seems that it's okay if we have 4 or 8 CPUs. But in a massive parallelism, we need more CPUs, and it seems be that it is not the correct way, because it's very sensitive to the part of the program which cannot be parallelized. For example, here we have only, I don't know if, here we have only 5% of the program which cannot be parallelized, and the performance is not increasing for approximately 1,000 CPUs. And of course today we have computer with 700,000 of CPUs. Then we can see that it will not help this amount of CPUs to go faster. Then we think that the way is the step back to pre-von Neumann architecture, when we have the separate block, and in which the memory is not disjoint from the CPU, because another bottleneck is the time consumption. If we move the instruction from the memory, we calculate into CPU and we send back to result in the memory. It takes some time, and this is the bottleneck in performance of computer. Then solution will be massive parallel architecture, in which we will have the blocks in which we can calculate separately, and in the best situation we will have in this block the permanent data which we will use for calculation to avoid this movement of data. And this is the concept of fuzzy logic circuit, where each instruction is in a specific block calculated, and these blocks are interconnected in the network, like as we have seen in ENIAC computer. then how many elementary circuits we have for each calculation, then so many calculation goes in parallel. Then this is the way how to obtain the massive parallelism, that we can implement each fuzzy logic function separately in some logic block. Of course, we have two types of program which have to run on such as hardware. One was presented here, which is approximated reasoning given by some implications. I think that in this kind of programming, in first step, the human elaborate some data, and from this data we mine some rules, and then we write these rules, and then we like to implement these rules back to the hardware. Another kind of programming is just put the data into machine and let the machine to extract the rules. And I think the successful way how to do that is evolutionary programming. Then we can find the structure of the fuzzy logic network which will satisfy some goal which we'd like to obtain by this structure. For example, here we have one example for speech recognition. Then when we send some data from voice spectra to the fuzzy logic circuit, and then we can recognize some vowels. Then this is, we made some simulation experiments with buildings such as fuzzy logic systems with different kind of logics. Here, as an example, there are some results to have idea how many elementary functions we need for such as recognition. Then we can see at the beginning we are starting with 50 functions to build the complete function. But anyhow, the accuracy is quite bad. It is approximately 79%. But if we train the network and we add a new elementary function to the network, then we can reach higher, and we see that we obtain this decreasing of 6% of success by 2,000 of elementary function. Then it's really a massive parallel network in which we have 2,000 elementary implementations of the fuzzy logic of functions. We make some decision about which logic will be applied. Here is example for good logic extended by average function. This I used only to show that for application we need really the massive parallel network. Another interesting thing what I'd like to show here is in genetic algorithm that we can see that there was increasing of the function and decreasing of the number of the fuzzy logic functions. It means that even if we obtain the simpler structure, then we obtain the higher accuracy of the recognition. My interpretation is that in this case, in this step, we leave some local minima and we go to another point of the space by step. Then this is quite good property of genetic algorithm, that it can overcome the local minima to go to the global minimum. Well, here I use another picture from the analog computer, and here is documented that when I started at university, I also obtained some diploma for programming of analog computer. This is the old time, but anyhow, this is again something like was ENIAC, that the program is given by wiring here. If you make some wiring between these blocks, then you put a program to the machine. Then I think that this is the way for the massive parallel computing, that the program should be given by the structure, not by the data. Well, another bottleneck what we can find in implementation is the way how the fuzzy logic is implemented. Quite common way today is by implementation by field programmable gate arrays. But anyhow, I think that it didn't take all the power of the fuzzy logic, because even field programmable gate arrays are Boolean machines, and if we like implement the fuzziness, then we use the Boolean numbers to implement the real numbers. Yeah, then I think that the future will be in analog implementation of the values. Today, the analog implementations are based on transistor. Before it was bipolar transistor. Today it is unipolar transistor, which bring us higher exploitation of the substrate. But if it is bipolar or unipolar transistor, there still is one bottleneck. It is not the bottleneck of the size, because until today the Moor law is running, and the density of transistor in square millimeter is exponentially increasing, and today the smallest transistor is in nano size. It was provided 22 nanometer transistor, but there is known, and some lab has also the 14, but it was not published yet. Then from the first transistor to today's transistor, it's really exponential progress, and we can see that this transistor is on the Moor line, which may be continue in the future. But what is the limit? But a limit is, of course, the atomic size or molecular size. Then today there are experiments with transistor with one molecule, but it's a limit. Then the classical transistor should have at least one molecule to operate. Then we have some limit of the Moore law, and in the future it is era of quantum computing, which can go down to the one molecule size. But anyhow, today we are still in nano size, and we have to use this technology to build fuzzy logic system. Performance of the computing is also increasing exponentially. Even they show the same half time, 1.5 years, as it is for Moore laws. And if we look for the most powerful computers, that it's really exponential growth of performance. Then this optimistic view is that, okay, in the near future we will obtain performance of the brain. Then what is the problem? It's not problem of density, it's not problem of performance, but it's a problem of energy consumption. Here is Koomey's law, which is very optimistic, and this law saying that electrical efficiency has doubled every 1.5 years. It is the same time as the performance, but something is wrong, because if all the three laws are true, then we cannot understand why the first computer needed 150 kilowatt of power, and today computer, the most powerful computer, needs 12 megawatts of power. Then probably something is not correct, because we see that the power is increasing with performance. And if we need more performance, probably in this way we will need more power than 12 megawatts. Then if we compare it with a brain with between 10 to 20 watts, that's it's really big difference. Then we are trying to obtain the similar performance and as we have in our head, but the energy consumption is incomparable. Then this is the main problem if we implement this massive parallelism into a real machine, that we cannot imagine that we will talk with some machine who will have some power plants behind it. Yeah, then what we are looking for is more efficient calculation than we have today with transistors. And why with transistors? Because it is known then for calculation with transistor we have some limits, and one limit is limit given by entropy, and I'd like show the Feynman explanation of this limit. And the question is how many energy we need to write one bit of information, and the Feynman proposed this very simple explanation. Then we can imagine that we have a box with one molecule of gas, and if the molecule is on the left side it means 1, and if the molecule is on the right side it means the 0. Then one way how to write to the box 0 is to put this wall to the middle, and then we will for sure have the molecule on the right side, and the 0 will be written to this box. Then it's quite easy calculation how much energy is needed to push the wall to the middle. I like save some time behind because we are behind the schedule. I will not explain in details, but we can obtain the law for ideal gas, and if we put one molecule here, then we can obtain that we need approximately 3 zeptojoules for this movement. Then this is the thermodynamical limit, how many energy we need to write one bit to the machine or to the memory. And where we are today, if we forecast the future by this Koomey's law, then we can calculate that from 1 kilowatt hour we may obtain approximately 4 times 10 over 19 megaflops per second, and it gives this figure. Then we will reach the thermodynamical limit approximately in 20 years, something like that. Then it seems that Moor's law we will reach the limit. The Koomey's law will also reach the limit. Then, as I said, Moor's law may be continued by quantum computing, but how we will continue over the thermodynamical limit. It is also known, and the way is going through reversible computing. Here is an example where we are today. Then today we are approximately here with nanotechnology, and this is the thermodynamical limit. On this picture is also the quantum limit, which is given by Heisenberg principle, but it is not placed correctly. But to have it in one figure, it is postponed 12 exponent 12 times more, because we can see here is the limit for transistor, and here is the limit for quantum computing, which is quite different number. But in both limits we can see that the energy is dependent also on the time, how much time we need to write one bit into memory. Then if we have longer time, then of course we can do it with lower energy. If we like obtain the short time, then we have to use the higher energy to write the bit. What we can expect from nanotechnology instead of transistor? This is one element which seems to be very interesting for the future, and this is memory resistor, also known today as a memristor. I will use the definition from Leon Chua, who called the memristor any two-terminal non-volatile memory device element based on resistance switching. Then here there are some advantages in this definition. First of all, this is this non-volatility. It is the main difference from transistor, because if you like keep logical 1 or logical 0 in transistor, you need some power for that. But non-volatility means that we need energy only for change of the value, but not for keeping the value in the memory. We know it today in flash memories. Yeah, then this is what we are looking for. We are looking for non-volatility. It means that no energy is needed to remember information. That is important property of the circuit, because we can spare a lot of energy if we don't need energy for memory, only for calculation. This element is known since 1960, but anyhow the most popular is since 98, when the HP lab proposed titanium oxide memristor as a Chua's memristor, which was described theoretically in 1971. Then from that time became the memristor very popular, and there are many articles about the technology of the memristor and also application of the memristor. Then what is the memristor? Then we can use the original paper of HP to explain the function of the memristor. Then we have again a box and with some resistance, and there are two areas. One area is doped by oxygen ions, and another area is undoped. And this doped area has lower resistance than undoped area. And if the current is flowing in this direction, then these ions are moving to the undoped area and build a bridge between these two electrodes, and then we have the on state of the memristor, which has a low resistance. If the current is flowing in the opposite side, then these ions are moving back to this area, and we have no conductive bridge between these electrodes, and this is the high resistance state of this element. And of course we need energy only for the movement of ions. Then if we keep the off state or on state, there is no ion movements and we need no energy to keep the state. Then this is non-volatile elements which will also keep in the memory the on state or off state. Here is the old paper of the Argel, which shows this property in 67, but since this HP paper, there is a lot of paper who are showing that memristors are everywhere. Then in this paper they found a memristor in polymeric material. In this paper they found a memristor in skin. Another paper shows also we have memristors in blood. Then now we are finding a memristor really everywhere. As it seems to be very natural, this non-volatility will be used for the new type of memories, because by nanotechnology we may obtain the higher density as we have today in flash memories. Then in near future it is expected that the memristor memories will come to the market, and here is the patent of Samsung, who is holder of such a device. And Samsung didn't publish the day when they introduced this memory, but HP announced it for 2014. Originally it was 2013, but a month ago it was postponed 1 year later, because it seems that this technology it's not so stable today, and another research is needed. Well, how can be applied this memristors element? First of all, it can be applied for Boolean logic, and it may be used instead of transistor to make Boolean circuits. Another approach is to use instead of synapse in neural networks, and this is quite a big movement in this way to build synaptic networks based on memristors, and this is known as neuromorphic computing today, and there are big projects in the US and also in Europe to build such as massive neuromorphic networks for computing. There are another examples, but it is only what was found, but it is not used for another examples. It was found that memristor grids can calculate the edges in the picture, or vice versa, may be used for regulation of brightness. Another example which is very interesting is solving the maze, because it gives an example of massive parallel approach to computing, and the maze have 2 doors, and in the Memristor grid we can set a system of wall in the maze, and then when we put the voltage in one gate and ground to another gate, then we obtain directly in the state of Memristor the route between 2 gates. And because all Memristors are working parallel, there is no problem to obtain the more large maze for solving. Then this is what we are looking for, how to use this idea of massively parallel computing. It is also known that the Memristor grid can be used for fuzzification. But in this paper was written one sentence which was quite pessimistic. Then it is evident that the construction of large-scale system like human brain based on this inference method is very hard, if not possible. Then it seems to be very pessimistic, but we have found that it is possible, and our approach is that if we build such a circuit, small circuit, and we put 2 values A and B, then in the middle we can obtain the maximum of these 2 values, or in another circuit we can obtain the minimum of these 2 values. Then based on that we propose to make the parallel circuit for these good logic networks. But what is the problem is problem with negation. We didn't find how to make a negation with Memristor, and another problem what we have with negation is if I show advantage of this circuit, that these circuits are passive, that there is no power source. Then these circuits can calculate the fuzzy logic function without any external power. The only power which is needed is power of inputs. Then this is the fully passive network, but of course it is impossible make the strong negation with passive network, because we need, if the value have 0, then we have to obtain the 1 as a negation. And how to obtain from 0 energy 1? That is impossible. Then it is impossible to realize the negation with the passive network. Then we try to solve this problem, and there are several ways how to solve it. First way is use, instead of strong negation, the weak negation, and this is what we also simulated, and we obtain the similar results as we have obtained before with strong negation. Then it seems to be that this is not limit for using negation. Another thing is using the Morgan law and to build in parallel the dual system. Then it is enough if we have negations of the input values. But inside all the network we do not need negation, because negation we have in dual system, and if we need negation we just bring it from the dual system and vice versa. And this leads to such as general architecture of the inference engine, where here by the classical computers maybe program the rules, but the implementation of these rules itself will be done by Memristors, and in this way we can build a massive parallel network. Here is shown that we need two systems which will be dual, and then for each input we need some inverters to obtain the negation, and then we need this cross part to bring negated values to the other half of the system. Then this seems to be to us the general architecture of such as computation. Another chance may be given by intuitionistic fuzzy logic, because if we have true degree and falsity degree, then negation is only changing the position of them, and it's very similar what we are doing in dual system. Then it is easy to build such a system because we don't need even inventors, but of course at the input we need to obtain some falsity degree for input values, and there may be different ways how to evaluate these degrees from the data itself. And this intuitionistic approach leads to the same architecture as I presented before by the Morgan law, and again then we don't need the inverters at the input, but we need the falsity degrees of the values at the input. And if we don't need the energy for calculation, then we can make the fully passive network. Then this is seems to be very interesting, that we can build a fully passive system which don't need extra power. Then we can build such a system into deep water or in the space or somewhere where we have problem to bring the energy, because such a system needs the energy only from some active sensors at the input, and that's all. Another nice property which we are studying is, I call it déjà vu property. Then we need the energy to bring memristors to on or to off states. But if the first step we set the memristors to these states, and we obtain another data which have the same relation between them, then the memristor will keep the same states as before, and we need no energy to change the state of memristor, and therefore we obtain a very fast response. Then of course, in this case, we need some time to reach the limit, but if the relation is the same, we don't need another time to reach the limit, but we obtain the result immediately. Then this is very nice property of such a circuit, and we are looking how to again use it for new form of programming, because one way of programming is to set the memristor to some value, but another way of programming is only giving the example of pattern to the network. And for similar pattern in the next step, you don't need much energy, but you obtain a result immediately that this pattern is similar to the previous one. Then we can program by offering patterns to the system, and then we can obtain different circuits which can recognize these patterns with very low energy and in very short time. Then we are studying now this property of the system. Another nice property is similar, that if we set the memristors to some values, then if we use the inputs with a lower voltage than is some threshold, then the memristor cannot be changed. The set state of memristor will be kept on the same, and this may be used for reversible computing. I have mentioned that today is a hope that reversible computing will overcome this thermodynamical limit, because the principle of reversible computing is that the function will not decrease the entropy. Then the same entropy as we have in the input, we will have also at the output. That this is one-to-one transform, and we can also have the inverse transform. Then in this case the entropy is the same, and there is no need for energy dissipation. It is known that there are several universal gates on which may be based, such as logic networks for Boolean logic, but we have found that the same may be done also for fuzzy logic. Then we can also set the basic circuit to two states, similar as it is in Friedkin gate. In Friedkin gate there are two states. One is direct state given by 0 in the control bit, or it is exchange position of the bits if the bit is 1. And we have found that the similar property we can obtain also here by memristors. Then we can, by initially settings, also bring the circuit to these two states and obtain again the gate which will be not dissipate the energy, but it is for all the range from 0 to the threshold voltage. And how to use this reversible computing, I'd like to show that it's really possible to use it similar like for maze problem solving. that we need to have the way from left to right, as well as way from right to left, and then we can find in maze we can find the way, and here we can find the inverse function. Then, for example, from this basic gate, we can build the sorting network, and if in the first step we bring the voltages in the input and we obtain the sorted voltages at the output, then in the second step, if we put the voltage to the first output, then we can find where was the maximum within these inputs. Then we can calculate the inverse function of maximum. And it seems it's very useful to have a network which can find the argument maximum in 2 steps, because for Neuman architecture it is the time-consuming program which can find the argument maximum. Then in this way it will be possible to solve the short path problem in the graph, or to apply the Bellman principle to control problems, because it is based on the same idea that in one way we will find the minimum, and the opposite way we will find where the minimum is. Then this is again implementation what we are studying. Until now we make only simulation at our university because we have no nanotechnology clean rooms, but we cooperate with other university who have these clean rooms, and we are trying to build these basic blocks and make experiment to learn behavior of such a solution. Then this is the basic idea for pattern recognition, which will be built in 2 steps. In the first step it is pattern recognition of instant pattern, but in second level we'd like also make some way of time steps or time stamps, which can be found in non-stable processes. Then our aim is to recognize also some non-stationary processes, not only the stationary processes. Then thank you very much for your attention.